Hi, my name is Ivan. In this video, I'm glad to present our work towards a unified Copernicus foundation model for Earth vision. This work aims at pushing the frontier of Earth observation foundation models by extending data, model, benchmark, and embeddings across a series of satellites. Let me start with a quick primer. Earth observation focuses on observing the Earth from platforms like drones, airplanes, and satellites. Beyond the overhead viewpoint, one key feature of EO is its multisensory signals across the spectrum, complementing each other for various tasks. With more and more satellites entering into space, EO data volume is growing rapidly. For example, European Space Agency's Copernicus program is the largest environmental monitoring program in the world. At the heart of that, the Sentinel satellites provide tens of terabytes of data every single day, addressing today's key environmental challenges like urbanization, natural disasters, and climate change. This availability of big data sparks a hot trend of research on general-purpose foundation models in the past few years. Typically, these are neural networks pre-trained on broad unlabeled data using self-supervised learning techniques. Despite the momentum, current EO foundation models face limitations along three dimensions. First, the diversity of sensors during pre-training is often narrow. Second, model architectures are typically designed for fixed spectral channels. And third, evaluation breadths are often shallow, covering only few task types or sensors. To address these, we introduce Copernicus foundation model with a series of contributions aligned to these dimensions. In an overview, these include a large-scale pre-training dataset, a unified foundation model, a comprehensive benchmark, and a global embedding dataset. Let me introduce them step by step. Copernicus Pre-Train is a unified pre-training dataset spanning all major Sentinel missions, plus digital elevation models. The dataset contains 18 million images pairing 8 distinct modalities, organized into dense regional grids. Images are aligned spatial-temporally with multi-modal time series. For low-resolution modalities like Sentinel-3 and 5P, each patch spans the whole grid. For high-resolution ones like Sentinel-1 and 2, we subsample local patches using a mix of Gaussian and uniform sampling strategies to balance the redundancy and diversity. Geographically, the dataset covers almost the entire land and nearshore oceans, including polar regions which was rarely covered by previous datasets. Based on the dataset, we propose a unified foundation model that ingests any image modality plus metadata. Two core designs made this possible. First, dynamic patch embedding so the model can tokenize arbitrary spectral layouts and resolutions, and second, unified Fourier encoding so the model can condition on metadata. During training, one image for each modality is sampled from a common grid cell, which is then patchified by a spectral or variable hyper network based on the modality's spectral response or variable name. Further, metadata encodings are incorporated into the patch tokens to be fed into transformer blocks. Let's have a closer look at hypernetworks. For spectral input such as RGB and multispectral, we encode wavelengths and bandwidth values into a set of vectors, which then go through MLP and attention layers to get flattened corner weights. These weights are reshaped into the convolutional corner for patch embedding. For non-spectral input, there's no quantitative attributes to encode. We thus use a language model to encode variable names and fit them into a similar hypernetwork. Following FlexiVIT, we also adaptively resize the corner weights to accommodate different input with varying scales. In addition to images, we integrate important metadata into the model by adding their encoded vectors onto positional encodings. This enables the model to reason about where, when, and how big area the observation was made. To reflect real-world scenarios where the metadata can be incomplete, we apply stochastic metadata dropout during training. A learnable token is used in these cases. For pre-training, we use masked image modeling across modalities as the primary objective, with an auxiliary distillation loss that aligns the RGB subspace to that of V2, anchoring our representations to strong natural image priors. We compare Copernicus FM with state-of-the-art foundation models on Copernicus Bench, a newly curated benchmark with 15 hierarchical downstream tasks across modalities. The results demonstrate our model's consistent benefits on all tasks, especially on new sensors. Last but not least, we introduce a global embedding dataset. For each grid cell in Copernicus pre-train, we fuse Copernicus FM embeddings across all available modalities into one embedding vector, counting towards 310,000 vectors for the globe. In spirit, this functions like a virtual satellite producing condensed surface descriptors, so downstream users can work with ready-to-use vectors instead of reprocessing raw imagery. Another exciting property of these embeddings is their potential to link Earth's surface and atmosphere. A toy example of predicting 6 climate drivers from geocoordinates verifies such benefits, where adding embeddings help produce finer and more accurate maps. This suggests that surface embeddings can act as strong priors for climate and even weather research. In conclusion, we present a series of efforts towards next-generation Earth observation foundation models, including pre-training dataset, unified foundation model, evaluation benchmark, and foundation model-derived satellite embeddings. All data and models are publicly available. You can scan this QR code to check them out. If you are interested, you are also welcome to read the paper and come to my personal session for the discussion. Thanks a lot.